Hi, everyone. I just wanted to post a quick video about the stuff that's in the homework for Chapter 3 and Chapter 4, which has been posted on Wiley Plus, especially since I had to miss Friday this week. So I'm going to go ahead and bring up a PowerPoint and write on that. And what I'm going to do is kind of go through the two-dimensional motion and talk about not the vector problems. There are actually vector problems in the Chapter 3, Chapter 4 homework, but I want to kind of focus on the projectile motion type problems. And so let me go ahead and get that here. So again, talking about motion in two dimensions, first thing I want to kind of do is just look at the definitions again. And when we define our quantities that are used for motion, they're very much the same for one-dimensional motion, except they now have an X and a Y component. So for example, right, if we wanted to find the position, we would define it as a position vector with an X component, which would kind of be the X coordinate, and also a Y component, which would just be the Y component of the particle that's moving around. So if I were to make a graph here, I'd have an X and a Y coordinate, and my particle would be here, and R would be the vector that points from the origin to that point. If the particle moves over here, let's say, well, now I'd have an initial position vector and a final position vector. And if I took the difference of those two, R final minus R initial, this would give me the displacement vector, which I'll write as delta R, which is really just the difference. And if you study it for a bit and look at the tip to tail method, here is my displacement. It just goes from where my initial position vector was to where my final position vector is. So it really is just telling me how I moved, right? Both in the X and the Y direction. So again, I have X and Y components for these. And right, again, to get the delta X, I would only subtract my X final minus my X initial. And to get the Y component, subtract my Y final minus Y initial. I would never mix the I hats and the J hats or the X and Y components. And again, just to define our velocity, we would have delta R over delta T. Anytime you divide a vector by a number, for example, dividing by a time of 3 seconds, 5 seconds, whatever it is, I just divide the components. So I'd have delta X over delta T I hat plus delta Y over delta T J hat. And so you can see I've got a sort of a one-dimensional X displacement and a one-dimensional Y displacement, and they form the components of the two-dimensional velocity vector. If I did want the instantaneous velocity, I would go ahead and have to take derivatives. And in order to do that, it's very simple. I just take the derivative of my position versus time with respect to time. But to do that, I just take each component's derivative individually. So I'd have dx dt I hat plus dy dt j hat. So hopefully you can see that all the operations I ever do on a vector, I have two operations, one on each component separately. And again, I could do the same thing in defining my acceleration. I would take the derivative with respect to the velocity vector. Now I'd have an initial and final velocity, but it would just be dvx dt, where vx would be the dx dt, right? It's the x component of the velocity. So it's really a second derivative. And then dvy dt, j hat. So writing it in second derivative form, I'd have d squared x dt squared I hat plus d squared y dt squared j hat. So hopefully this really emphasizes that anytime I take derivatives, I multiply or divide by vectors, I just do the same thing to both components. And this is the way it's always going to work for vectors. We'll deal with a lot of vectors in the future. Some of the problems in the chapter 3, chapter 4 homework that I assigned through Wiley Plus, you'll be calculating components for different vectors, but you add vectors the same way. You calculate the components and then add the x components and add the y components. So I'm going to go ahead and move on now to the projectile motion. How would I deal with a projectile motion problem? So what I mean by this is that now instead of a one-dimensional motion, we have a two-dimensional motion where maybe it's a ball flying through the air. And the basic idea is that we're going to use the idea of vector components again, right? We're going to realize that the x component doesn't depend on the y component. So we're going to have motion in the x direction. And I could write this all out in I hat, j hat form, but the way I'm going to do this is I'm just going to separate the two directions. And if I look at the y direction motion of a ball or a projectile, it's really just going straight up and straight down. And we know how to deal with that. We've dealt with the free fall problem before, right? And so we can use all of our free fall equations. We just now have to realize we're talking about the y components of the velocity and of the acceleration and everything. Right, so for example, our delta y equals our average y velocity. So v final y plus v initial y over 2 times t. So I'm always dealing just with the y components. But this is just our kinematic equations for free fall. Let me write them all out there. So anytime you're just looking at the y components or the y motion, it's just like the free fall problems from chapter 2. What about the x direction or the x components? So in the x direction, is it a constant acceleration? Well, yes, it is. In fact, if we neglect air resistance, as we are going to do, we're going to we'll talk about air resistance maybe a little later, but for now, we're going to say acceleration is 0 because there's no horizontal forces, nothing pushing it, slowing it down, or speeding it up in the x direction. So if our acceleration is equal to 0, then our x component of velocity, which we might write as an initial, is going to equal our final. It's equal to a constant. So I still can apply the kinematic equations to this situation, but my acceleration is 0. So if I go over here, for example, this equation, this third equation, I would have delta x equals vix t, but my a would be 0, not negative g. So the only equation I actually have is this for my x direction motion, or for my x components. So what's going to happen in projectile motion is that we are going to have really two problems, right? One problem is the free fall up and down, where we can apply our free fall kinematic equations. The other is a constant velocity motion horizontally. Now the motion's connected, and the way it's connected is through the time. For example, if I wanted to know the x and y positions of a particle at a certain place, right, the time is going to be the same. Right? And what will happen in some problems is that if you want to figure out something about another component, right? If you, for example, you could solve for the time in the y direction and then plug that into the x equation over here and determine the variables in the x direction, or the x component variables. That's kind of really one of the basic ideas of the projectile motion problems. But I think the best way to deal with this, or to look at this, is to go ahead and look at a couple of example problems. So the first example one is what I would call a zero launch angle problem. In this problem, the ball is just rolling off of a flat table. All right, so the ball is going to come and it's going to roll off of the table at some speed. And it tells us the dimensions of the table. Well, the height of the table is 1.2 meters. And it tells us after it leaves the edge of the table, it travels a distance of 1.8 meters, right, before hitting the ground over here. And the question is, knowing those sort of measurements, what is the initial velocity that it left the table with? If I think about it a little bit, there is only an x component, right? Actually, VIY must be 0 because it's not moving up or down as it leaves the table. Okay, so how am I going to do this problem? I want to figure out that initial velocity. Well, thinking about it a little more, if I want the x component, there's only one equation. Delta x equals VIXT. Right? That's the only equation that I can use to find my x component of velocity. Now, I do know what delta x is. Delta x is 1.8 meters. So the problem I have is, what is the time? Right? Because if I knew the time, I could solve for VIX. Just take delta x over t. And I know, again, delta x. So how do I get the time? Well, to get the time, I can look at the y direction. And I'm going to consider free fall. So if I look in the free fall in the y direction, again, right, VIY is 0. I always know g, right? The acceleration, the y component of acceleration is -9 or 9.8 meters per second squared. And in this particular situation, I also know what delta y is. Delta y is -1.2 meters. Okay. Again, it's negative because it's falling downward. The change in y is negative, in the negative downward direction. So the question is, what is the time? Well, solve for t. And then I'm going to plug it back into here. And I will calculate my initial speed. So that's my sort of two-step plan. Use the y component equations, the free fall, to solve for the time that it takes basically to just fall straight down from the edge of the table, right? The time would be the same if you just dropped it. But then use that time in my x component equation to solve for the initial speed. So let's go ahead and do that, execute that. To get the time, if I go back and I look at my variables, right, I have an initial velocity in the y direction. I know g, I know delta y, and I know I want to solve for t. So looking at my equations, looks like I could use that one, right? It has all of those variables in it. So let's go ahead and use delta y equals VIYT minus 1/2 GT squared. And again, I like to get a formula. And so the easiest way to get a formula, though, is to plug in that VIY is 0 because it doesn't have an initial y component. So if I solve for t, just do a little algebra, I'm going to get -2 delta y and divide by g, but then I have to take a square root of that. So there's my expression for my time. I might wonder, okay, well, that negative sign worries me a little bit because it's under a square root. But if I recall, my delta y is going to be -2, right? Because we're going down and the negatives will cancel and I should end up with a positive time. So I think everything will work out there. But then the next part of my plan is to get VIX, which is delta x over t. And again, just writing the formula, right? If I took delta x over t, I would get this delta x divided by the square root stuff, but that's the same as inverting it. So g over -2 delta y. Now I can plug in my numbers at this point. I can plug in that g is 9.8, delta x, let's go ahead and do it. It's delta x was 1.8. G is 9.8 meters per second squared. I get over -2, and then what delta y is -1.2 meters. And I think this comes out to be about 3.64 meters per second. Okay, so hopefully that shows you that I really do two separate problems, and the two separate problems are connected through the time. Just to finish this here, again, you know, if I have a formula, I can check my answer. I could check my units and verify that they do come out to meters per second, which you can do. You can verify this, that the units are meters per second. Another thing I could ask is, well, would the speed be faster if I change some of the variables? What if the delta x that I measured were bigger, right? So it went further horizontally. Yeah, it should be a bigger speed. VIX should be larger, and that's what happens in my formula. What if delta y is bigger? So it's starting from a higher place. Well, then delta, it's going to fall further. The time is going to be bigger. The initial speed will be bigger as well. Right? Oh, wait a second. Sorry. Actually, I have that a little wrong here, right? If it starts from a delta, a y that's bigger, but the delta x remains the same, it's actually got to be going slower. And in fact, that's what you see from this equation here. Delta y getting bigger means a slower speed. So I have to think about that a little bit, right? You would think the delta y would increase the time, which it does. But if the delta x doesn't change, the initial speed's got to be smaller. Okay, so that one was a little bit of thought I had to put into it. But this shows you, again, if I do have a formula, I can sort of check those sort of things. All right, so I want to do another problem. This is the last one for this video. This is what I'd call a general launch angle problem. And in this case, you're launching a projectile at an angle instead of horizontally. The biggest difference here is that you're now going to have a y component of your initial velocity. Right? So here I have a cannonball, and we're just going to say it's fired from the ground level at an angle of 30 degrees and a speed of 100 meters per second. And so just like any vector, I'm going to have an x component, VIX, and a y component. Now to get those components, just like any vector, I have to use trig. So my VIX is my VI, which is the 100 meters per second, cosine of 30, right? Because it is the adjacent side of this triangle. Plugging in the numbers, I think you get about 86 meters per second in the x direction. And then VIY is the VI sine of 30. Because again, it is the opposite side of the 30-degree angle. Plugging in my 100 meters per second and 30 degrees, you should get 50 meters per second. But otherwise, this problem is very similar, right? And so the part A of this question is, what is the maximum height of the cannonball? So I have to think again, if I want the maximum height, I don't even need to use the x direction at all. I am just talking about it going up and reaching its maximum height and then coming back down. What it does horizontally in that time does not affect the maximum height or the y components at all. So this is just a free fall problem. The free fall problem, just like chapter 2, right? So what we want is delta y equals h max, right? Our maximum height. What is the displacement when it gets to its highest point? Now the condition that it reaches its highest point is that its final velocity y component is 0. Right? It has stopped moving upward, is just on the verge of coming back down. So that's its maximum height. Other things we do know VIY, and it's our 50 meters per second. And we always know G. So once again, going back to those kinematic equations, right? I don't have the time in this problem or in the variables that I've written out here. So looking back a couple slides here, the only equation without the time is this one, the last one. So I'm going to try to use that. So I'm going to use my v final y squared equals v initial y squared minus 2g delta y. Now again, I have a 0 here, but it's the final velocity is 0 in the y direction. So my delta y, which is my maximum height, I'm just going to solve for, right? So I'm going to add over the 2g delta y and then divide by 2g. So I get VIY squared over 2g. And if I plug in the numbers, right, I'm just plugging in the 50 meters per second for the VIY and 9.8 for the g, you'll get a maximum height of 510 meters. So again, I just want to emphasize, I didn't have to use the x components at all for this problem, because I was only talking about y, how high did it go? I wasn't talking about how far horizontally it went. Not yet anyway. In part B, we'll do that. Again, you know, I got a formula for it, and you could check the units. You could do some evaluation of that too. An interesting thing I see here is that the height gets bigger as the velocity squared. So if you shoot it up at 10 meters per second, it's going to go to a certain height. What if you shot it at 20 meters per second? Right, twice as fast. The square here is going to tell me it's going to go 4 times as high. That's kind of an interesting observation. We might come back to that later on when we talk about energy. But again, having the formula allows you to see things like this. So I want to emphasize it's good to get those formulas. But let's go ahead and look at part B here. And to do part B, what we're asking for is the range of the projectile. Now, when I say the range, what I imply is that it's going to go up to its maximum height and then come back down. And its range is the horizontal distance it covered in that flight, right? So it ends up at the same height that it started at. And so what that tells me is my displacement is 0, actually, right? It's gone up and come back down to the same height. So its delta y is 0. Now, I shouldn't say its displacement is 0, because it does have a delta x. It has an x component of displacement. And in fact, that's what we're looking for. Now, I'm going to kind of do this problem a little bit roundabout way. We found that the maximum height, right, we got a certain formula for that. If I think about this though, to get to the maximum height, it's going to take a certain amount of time. And then the problem is, okay, well, it's going to come back down. The amount of time that it takes to go up is going to equal the time that it takes to come back down. Right, so the time that it has gone to its maximum height equals the time that it takes back to come back down. So if I can get the time for the maximum height, then the total time that it takes to go from where it started to where it finished is equal to that, is twice that. So my goal is to get this time for the maximum height. And then if I want my delta x, it's the initial x component of speed times that 2-time height, right? The total time. So to get the time for the maximum height, right? Well, again, my final velocity is 0. It's actually I'm kind of going through this one a little quickly, but hopefully you see it's just an extension of the previous part A problem. Sorry, this should be a minus GT, right? My final velocity is 0. So T, just solving for T here, is VIY over G. Then my total time, which is twice this, is 2 VIY over G. So my delta X is just my VIX times that total time. And plugging in the numbers, right? My VIX was my 86, my VIY was 50, G is 9.8. I think you get a distance of about 2,000. See, I didn't write this down. So let's plug the numbers in. So I get 86 meters per second for this, times 2 times 50 for the y component of velocity, over 9.8 meters per second squared, right? Again, it's fairly easy to check the units there, but I do get a distance of 2,000 meters. So the cannonball goes a horizontal distance at a land 2,000 meters away, and we call that the range. Now, if you're shooting at the side of a mountain, right, your delta y wouldn't be 0, and it would be a different problem, but you could solve it maybe in a similar way. It may be a little bit hard because the time would not be equal, right? The maximum height to when it hits the ground. There is another way to do this problem, and I believe this is what they do in the book. So let me just go ahead and talk about that real quickly. The other way that you could do this problem is to just go ahead and use your delta y equals VIY t minus 1/2 GT squared. Since delta y equals 0, this is equal to 0, and you can solve for t. This will give you the total time. It'll tell you not the time just to go to the maximum height, but the total time that it takes to cover the whole distance, right? And get back to its initial height where delta y is 0. And then you could use delta x equals VIXT. So you don't have to do the problem any particular way. Sometimes there are certain advantages, sometimes there are not. But you can choose whatever equations will get you to the answer. But again, I do want to emphasize, I'm always looking at the y direction and then looking at the x direction. Sometimes I'll be given information from the x direction. You know, if I was given delta x and VIX, I could solve for t here and maybe plug it into the y direction. But the time is always what's connecting the two components. Okay, so I'm going to stop there. Hopefully this will give you a lot of help or some help in solving these projectile motion problems, especially since we don't have class on Monday this week. So if you do have questions, please email me. I'll be around and I'll try to answer questions throughout the week, even on the holidays. So, all right, thanks. Bye.